Next, we're going to derive the formula for a one proportion z interval. This is the first confidence interval we're going to look at, and it basically sets the stage for all the other ones we're going to look at later on. The purpose of this is to estimate a population proportion p. So we're going to use a confidence interval built around a sample proportion rather, to estimate a population proportion. In order to do that, we need to use the sampling distribution of p hat, the sample proportion. And that sampling distribution is subject to these conditions. You've seen these from Unit 9. We have to have a simple random sample, a population at least 10 times the sample size, and then n times p hat greater than or equal to 10, and n times 1 minus p hat greater than or equal to 10. Now in Unit 9, these values for p, where we have p hat, were p, the population proportion, and we don't know what that is. So we're trying to estimate it with p hat, and we're going to use p hat in here on condition number 3 to check that condition. Okay, so that's a little bit of a wrinkle, and it's different from what we did when we were doing the one proportion z test, where we used the null hypothesis value here and here. So it's a subtle difference, but it's an important one. Okay, now if these conditions are met, this is what the sampling distribution of p hat looks like. It'll be normal, with a mean equal to p, the true population proportion, and a standard deviation equal to the square root of p hat times 1 minus p hat over n. Now again, when we did the sampling distribution in Unit 9, this p hat was a p, and that p hat was a p. We don't know what p is, so we're using p hat instead. Now whenever you use sample data to estimate a standard deviation like that, you call it a standard error. So this right here, we're going to call the standard error of p hat, the standard error of our statistic, p hat. And we abbreviate it like this, capital S, capital E, subscript p hat, okay, just for the sake of brevity. Now here's how things look. Suppose we want to construct a 90 or C% confidence interval for p hat. We want to use our sampling distribution for p hat like this. We want to break off the middle C% of the area under that curve. Now the total area under that curve is 1, so this C% would be, a fraction of that. Now, according to this sampling distribution up here, the mean of p hat is p, and the standard error of p hat is this right here, which we'll abbreviate with SE of p hat. And to capture C% on either side of p, the center of that distribution, we have to go out z star times the standard error of p hat on either side. Okay, this tells us how many standard deviations to go, the z star, and then this tells us what the standard deviation is. So that's what we have to add on to p hat, or to p rather, to get the right boundary of this area, and we have to subtract that from p to get the left boundary of that area. Okay, and that's where the confidence interval is going to come from. Now, in C% of all the samples of a given size, p hat is going to be between those boundaries. The lower boundary, p minus z star times SE of p hat, and the upper boundary, p plus z star times SE of p hat. Okay, now we're going to do a little bit of work here, a little bit of inequalities. Okay, p hat is between these two boundaries. Now I'm going to take that left expression and I'm going to make p hat be greater than that. Okay, p hat has to be between the lower boundary and the upper boundary of that interval that I showed you in the graph a minute ago. And so p hat has to be greater than this, and p hat has to be less than that. Okay, this is the lower boundary of that interval that we saw, and this is the upper boundary of that interval that brackets that C%. Okay, now I'm going to add z star times SC of p hat to both sides of that, and that's going to give me this. P is going to be less than p hat plus z star times SC of p hat. I'm going to subtract this right here from both sides of that inequality, and I'm going to get that p is greater than p hat minus z star times SC of p hat. Now I'm going to put these two things together. This is the lower boundary for p, this is the upper boundary for p, and that is going to give me my confidence interval. Okay, so I basically took this, I moved it over here, that whole thing, and then I took that and I moved it over here, and I put them all together into one compound inequality. All right? Now, in C% of all the samples we can take of a given size, this interval from this boundary to that boundary will contain P in C% of all those samples. Okay? So that's what connects the boundaries of this interval to that level of confidence right there. Okay? Now typically what we do is, instead of writing our interval like that, we condense it down into one expression. And since these are the same, except that has a minus and that has a plus, we condense that down into p hat plus or minus z star times SC of p hat. And then we replace the SC of p hat with this square root of p hat times 1 minus p hat over n. And that'll give you your C% confidence interval for p.